So here we're going to quickly go through some air resistance problems and hints, and maybe quickly do a problem. I've written here some notes about how we should solve and approach each of these problems. We're going to need to draw a force diagram and then write whatever those forces are going to add up to being m times v dot. And then we'll separate our variables, which means we're going to need to get all the v stuff on one side of the equation. When we do that, we're going to want to determine if we want v of x or v of t. If we want to use v of x, then we'll say that v dot is v times dv dx. Then we'll do some integral calculus. We'll have an integral to do. We might need to use a table to look those up, or we might need to use u substitution. When we do our integral, we're not going to forget to add our constant of integration, because when we go to evaluate our boundary conditions, then we need to figure out exactly what that constant was supposed to be equal to in order to set the boundary condition. And then finally, we'll solve for the velocity as a function of time or the velocity as a function of the position. So as a quick first example, let's assume we're going to move along the horizontal direction, which we'll call the x direction, and that our only force will be equal to a linear air resistance force. So let's suppose our only force is minus mkv. So we're going to set that equal to mv dot. So if we want to first, let's say we want to solve for v as a function of t with v at 0 being equal to some speed v0. So what we have is v dot is minus kv when I cancel out the m's. V dot means dv dt is equal to minus kv. So I'm going to separate the variables this way. I'm going to say the dv over v is equal to minus k dt. So it's best to try to get those constants over to the other side next to the time if possible. So here I divided through by the v, and I multiplied over by the dt. When I integrate both sides, I have the natural log of the velocity is minus kt plus some constant. So here I've remembered to add my constant of integration, and that's important because I'm going to fix my constant of integration using my boundary condition. So the way I do that is when t is equal to 0, my velocity is v0. So apparently c is the natural log of v0. Now that I have my boundary condition, I can put that back in. So I'll write that over here. Now I have the natural log of v is minus kt plus the natural log of v0. And now I'm going to go to that fifth step, which was solving for v as a function of time. So I can write this as the natural log of v minus the natural log of v0 is minus kt. So the natural log of v over v0 is minus kt. So if I exponentiate both sides, v over v0 is e to the minus kt, or finally I would be able to write v is v0 e to the minus kt. So that's my final solution where I've solved for v as a function of time. Let's suppose I have the same problem, but now I want to find v as a function of x. So I have mv dot is minus mkv, like I did before. But now v dot is v dv dx. So I have v, the m's will cancel, dv dx is minus kv. Okay, well this is a little bit strange, but it looks like the velocity's canceled out too. So I get dv is minus k dx, and I can integrate both sides. And so v is minus k times x plus some constant. Now I haven't specified my boundary condition, so let me say that at x equals x0, v is equal to v0 is my boundary condition. So specifying this as my boundary condition means I come over here and I write v0 is minus k times x0 plus c. So c is therefore v0 minus k x0. If I go and substitute that back in, I would have v is minus kx plus v0 minus kx0. I don't know how exactly I want to rearrange this, so maybe I'll write this as v minus v0 is minus k, x minus... looks like I needed a plus sign here, right? If I solve this for... yep, I would need a plus sign there. So if I fix my sign error here, that becomes a plus sign. And then I have this nice little form here. And so we see that when x is equal to x0, v is equal to v0, and both sides, I get 0 equals 0 on both sides. And so, you know, this was sort of a simple looking problem. But that's how I would solve for v as a function of x. If I had a more complicated force on the right-hand side, I would do the exact same thing. Now, so these were the simplest possible ways of doing it. So let's suppose when you're doing the problem, if you're going to succeed in doing your air resistance problems, what you'll have is some v dot is some function of v. So let me define little f to be whatever capital F is divided by m. So my differential equation right now is some little f, which is a function of v, is equal to v dot. So in general, what I would have to do is I would write this as dv dt is whatever this function of v is. So dv divided by f of v is equal to dt, and then I can integrate both sides. So when your force here only depends on the velocity, then it's possible to separate the variables by pulling all of that over to the other side. So for instance, if I had a problem that had air resistance and I was, say, going downwards, so I had a downwards force of mg and an upwards force of, if down is, say, the positive direction, minus mkv, then the force is mg minus mkv. And so mv dot was mg minus mkv. Masses would all cancel out. And what we see is happening here is that we're seeing that we're getting v dot is g minus kv. Now the key is that you need to group the whole g minus kv. And so I'm going to write this as dv divided by g minus kv is equal to dt. In the same way that up here, I move the whole thing underneath, I'm going to group the whole part and bring it underneath. This particular integral I can do with u substitution. There might be other integrals which I might, that's not how you spell substitution. 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 There we go. That's closer. Some other integrals I might need to look up in an integral table. But I'm going to try to separate my variables in this way. Then I need to do my calculus and do my integral somehow. And then I need to evaluate my boundary condition.